Hello, everyone. I'm Alexandros, and today I'm going to present to you some of the results of our work on robust revenue maximization under minimal statistical information. This is a joint work with Yannis Giannakopoulos, also from the Technical University of Munich, and Diego Posas from the University of Lisbon. And let me jump straight into the motivation of our problem. And for this, we're going to use Myerson's optimal auction. So what's Myerson's optimal auction? We have n bidders and a seller auctioning a single item. And the bidders have some valuations over this item, and they draw these valuations from a prior joint probability distribution F. For this example, we're going to assume that the bidders draw the valuations independently, which means that F is a product distribution. And for simplicity, furthermore, we're going to assume that the bidders are identical. A reasonable question to ask in this context, from the perspective of the seller, is what is a revenue maximizing auction? What should I do in order to maximize my revenue? And Myerson came somewhat 40 years ago and gave a very elegant answer to this question and said that under some extra regularity assumption on the distribution, the seller should run a second price auction with a suitable chosen reserve price. And that's a very simple mechanism, and it's the best one among the space of all possible mechanisms that one can think of. Now, what's a very strong assumption here in order to obtain this result is that in order to choose this reserve price, the seller has to know in advance, has to have full knowledge of distribution F in advance. And that's arguably a very strong assumption in practical scenarios, and this is from where our work departs. So let me give some motivation. As we said before, exact knowledge of the distributions of the bidders is rare in practice. Instead, you might be able to obtain some distributional properties, but exactly determining the distribution might require enormous computational resources. Furthermore, and what has come to be known as Wilson's doctrine, and our work is in line with this doctrine, we should try to design mechanisms with based on as limited knowledge as possible on the bidder's valuation. That's going to give rise to mechanisms in auction design settings that we can apply to very broad scenarios. Furthermore, we want to capture scenarios here where since we're gonna base our mechanisms on statistics that we know of the distribution, we want to capture scenarios where the seller has no access to the underlying distribution. In particular, she cannot observe individual past data or something like that due to some type of data privacy, let's say. But she might be able to get statistical aggregates of this underlying data. Now here it's worth comparing this line of work with knowledge of the moments to another recent very beautiful line of work, which is based on sample access to the underlying distribution. So this line of work asks a question of if I can get samples from as a seller from the underlying distribution F that I don't know, how many samples should I get in order to design mechanisms that are near optimality, as if I knew the distribution in advance? So our line of work is incomparable with this for two reasons. First, from a practical perspective, we focus on these different type of scenarios when we don't have this access. And also, sometimes one might argue that it might be difficult to store and reason with a very large number of samples. And from a theoretical perspective, these works are based on different distributional assumptions. In particular, it has been shown that in this sampling complexity literature, you have to assume some type of independence on the distribution, regularity, or some upper bound of support in order to achieve meaningful results. In our work, we want to drop these assumptions, and instead we focus on others. So what's our setting? It's very simple. In the more general case, you can study a single additive buyer. The buyer has additive valuations over the items, and there are m possibly correlated items. And what's the prior knowledge of the seller? It's very minimal. She just knows the means and an upper bound on the standard deviations of each item's marginal distribution. This is how the whole mechanism works. So first, the seller, given this information on the marginals, announces a mechanism. And then an adversary, sometimes also called the nature, observes this mechanism and chooses the worst distribution for the seller among the set of eligible distributions, means the ones that respect the given statistics in the input. And well, after this happens, the seller observes her expected revenue. The question we want to ask in this setting is, given this type of information, can we still design simple mechanisms that can provide good approximation guarantees when we compare to the scenario where the seller knew the whole distribution F in advance and could fix a mechanism based on that knowledge? Let's look at a very simple example in order to be on the same page. So forget a bit about statistics, about means and standard deviations. Think of a single bidder, single item case, and of a very restricted adversary who is going to present to us, to the seller, one of the two following distributions. The seller knows that the adversary will present to her one of the two distributions. So the bidder draws her valuations for the item either from distribution 1, in which case her valuation is 1 with probability 1, or from distribution 2, in which case her valuation is 0 with probability half, and 2 with probability half as well. What we may first ask here, from the perspective of the seller, is what's the best deterministic pricing? In this case, it's going to be a posted price. So what's the best pricing here? If you look a bit at the distributions, it's not difficult to see that the seller should price at 1, in which case the adversary is going to respond with distribution 2 for an expected revenue of 1/2. Now let's shift our attention to randomized mechanisms. And what's probably the simplest randomized mechanism that we can think of? It's going to be a randomization over 2 posted price, that's all. So let's assume that the seller announced the following mechanism. She's gonna post a price of 1 with probability 2/3, or a price of 2 with probability 1/3. What will happen in this case? If the adversary responds with the distribution 1, the expected revenue of the seller is gonna be 2/3. And if the adversary plays distribution 2, when we have to do the simple calculations, bottom line, the expected revenue is going to be, for the seller, is going to be again 2/3. And this is an observation for our results also later. Observe that a very simple randomized mechanisms outperforms the best deterministic pricing. And we're going to see in the results also that randomizing in this case vastly helps hedge uncertainty. Some previous results in this line of work. So from the side of computer scientists, probably the whole idea of studying optimal auction design based on some statistics of the distribution started with Azar and Mikali with 2 subsequent papers. And they start from the simplest scenario, so single item, single bidder, and deterministic mechanisms. They first give an exact solution to the maximum expected revenue. And furthermore, they go on and provide some non-tight upper and lower bounds for the ratio. So the ratio of the optimal mechanism over F to the revenue of the deterministic mechanism over F. And these bounds grow quadratically in this ratio sigma over mu. A little bit later, Azardas Kalakis, Mikhail, and Weinberg generalize some of the above results to the case of n bidders single item. They do have slightly different assumptions, but again, they design the mechanism based on the assumption that the seller knows some parameters of the distribution. For example, what happens if the seller knows only the medians of the marginals? And for this case, they provide simultaneously revenue and social welfare approximation guarantees in some constrained environments under some extra assumptions of the distribution like regularity or monotone hazard rate. From the side of the economists, there is a paper from Carrasco et al. Which studies again this robust expected revenue and provides the optimal mechanism for the case of single item, single bidder, and now the richer space of randomized mechanisms. And a bit later on, there is a generalization of this result to n bidders as well. And very recently, also Sudstaltsev studies also a very similar setting. Again, maximum optimal revenue and bidders and single item, and comes up with the best deterministic mechanism in case the seller knows the means and an upper bound of the support of the distributions. What we need to observe in the above results and how it compares to our work is that none of the above is tailored. So the mechanisms that they design are not tailored to this ratio, to this ratio benchmark. And furthermore, we try to make a first step towards designing mechanisms for multi-item settings, since multi-item optimal optional design has proven to be very, very challenging. Let's move on to the main contributions of our paper. And now let's define a bit more formally our quantity of interest. This is what we're going to call the robust approximation ratio, which is what we described before. So the seller, given this prior knowledge, tries to fix the best possible randomized mechanism that you can come up with, and then the nature responds with a worst case distribution among the set of the eligible distributions for this mechanism. And the ratio is going to be the optimal revenue on F, on this chosen F of the adversary, over the revenue of the mechanism that the seller chose, again with respect to F. And our results we're going to term R, this ratio sigma over mu, which very often in the literature is referred to as the coefficient of variation, and it's essentially a measure of the dispersion of a distribution. So first, we start with the simplest case of single item, single bidder deterministic mechanisms, and we tighten the results from the work of Asar and Mikhaili by providing an exact answer. We said that the robust approximation ratio is exactly this rho, which roughly is 1 plus 4r squared. So it grows quadratically in the coefficient of variation. And we also provide the price that the seller should post in order to achieve this ratio. We continue with by studying randomized mechanisms, single item, single bidder. And in this case, we also give an asymptotically tight answer. So for randomized mechanism, the robust approximation ratio is this rho, which is roughly 1 plus a logarithm of 1 plus r squared. So it's logarithmic in R in particular. And we also provide a lower bound, and we show that our mechanism is asymptotically tight. Our mechanism, what we say randomized mechanism here, we simply mean randomization over posted prices, as shown in the example. Finally, we move on to the more general case when we have an additive buyer and m possible correlated items. And in this case, we show that the approximation ratio is again grows according to the logarithm of R max. R max is the coefficient of variation of the, let's say, worst item. So the item that has the maximum ratio of sigma over mu. How do we achieve this? It's a very simple mechanism. What you should do is just sell each item separately using the lottery, this randomization over posted prices of the previous year. Here we plot our results for the robust approximation ratio for small values of R for the deterministic and randomized case. What's very nice with our results is that that we provide closed form formulas for them. So in particular, we can even prove we can even plot the exact ratios for very small values of R. So left you can see deterministic, and on the right you can see how the randomized approximation ratio grows. And you can also see the lower bound. As we said, the lower bound is asymptotically tight in the case of randomized mechanisms. So for very small values of R, there is going to be this very small gap, but for slightly larger values of R, these two lines converge very quickly to each other. And it's worth mentioning here that in practical scenarios, we don't expect the coefficient of variation to be very big. So normally, the data that you observe don't have very large dispersion, which means that our mechanisms, even just knowing the means and an upper bound of standard deviations of the marginals, still get very good approximations, as you can see the plots. And for special class of distribution that we often encounter in the literature, like MHR or some type of regularity, this coefficient of variation is probably very small. For MHR, for example, it's always smaller or equal than 1. In general, we could say that if in a particular application we could bound the coefficient of variation by universal constants, then our approximation ratio in this sense is constant as well. For the remainder of the talk, I would like to focus a bit on the technically more challenging proof of our paper, which is the lower bound for this lower bound that proves that our randomized mechanism is asymptotically tight. And let's go through that for the case of single item, single bidder. How we prove lower bound here? We do it through a generalized Gauss principle. Gauss principle is used very often in the literature in order to prove lower bounds on the performance of randomized algorithm. On a high level, think of a cost minimization game. What Gauss principle says is that the performance, the expected cost of a randomized algorithm over the worst case input is not going to be better than the expected cost of a deterministic algorithm when we choose a distribution over inputs and then we fix the best deterministic algorithm on the distribution over inputs. And in particular, if we find the best randomized algorithm and the worst distribution over inputs, this is satisfied also with the quality. So let's use a Gauss principle and let's describe how this could apply in our setting. Let's parse this formula together. Don't pay so much attention to the notation. What this says is that on the left we have a robust approximation ratio. So the ratio, the performance on a game where the seller plays first by randomizing over posted prices, choosing a randomized mechanism, the INF, and the nature responds by choosing the worst case distribution, that's a SOUP. So the ratio that we're going to obtain from playing a game like that, this our game, is not going to be better than another game, than the ratio of another game, where the adversary plays first by choosing a distribution over inputs, and the seller responds by playing a deterministic mechanism, which in this case, single item, single bidder, is going to be a posted price. What's different now from the classical Gauss principle in our setting is that this randomization over inputs, since our inputs are probability distributions, there's going to be some sort of distribution over distributions, which gives which forms an even dimensional space. So we have to prove a type of Gauss principle from scratch in order to show that it also holds in this case, in this type of infinite dimensional space. Furthermore, we have to come up with a specific model of randomization to describe this distribution over distributions. And what we do is what is referred sometimes in the literature as mixture or contagious distribution. And when we come up with a mixture, then this gives rise to the posterior distribution, which is what we have to calculate in this new game. And you can think of the posterior distribution in the following sense. Think that we first start by drawing a probability distribution f according to some parameter epsilon that is also sampled from some probability distribution. And then we use this distribution f with the parameter epsilon in order to sample the value z. And that's going to be our posterior. On this posterior distribution, we need to come up with a mixture that gives us the possibility to calculate the optimal revenue and the revenue of the best deterministic mechanism on this posterior distribution. In this new game, if we can find a ratio that matches the ratio that our randomized mechanism obtains, then we have proven that our randomized mechanism is optimal in this setting. Let's have a glimpse into how we construct our mixture. Here is a way to do that. This is the probability distribution from where we draw our parameter epsilon. And then, as we said, we first, according to this parameter epsilon, we sample a probability distribution f with this parameter epsilon. And then we move on by drawing a value z from this f with parameter epsilon. These f's that we have constructed are 2-point mass distributions. So in particular, we have a mixture over 2-point mass distributions. And using this mixture, we can, with the process we described before, we can calculate our posterior distribution, G, which looks like that. And then obtain the optimal revenue with respect to G, and the revenue of our mechanism with respect to G, of the process price mechanism, of the best process price mechanism. What's nice to observe with this posterior distribution is that it is some type of truncated equal revenue with additional point masses at 0 and a mu over epsilon 0 for some suitably chosen epsilon 0. Well, in the literature, we have seen sometimes that the equal revenue distributions are the difficult instances for our mechanisms in different auction design settings. So what comes as a posterior from our mixture is not exactly an equal revenue, but it is an equal revenue for a subset of the support. And using this mixture, we can prove that the randomized mechanism for the single item, single beta case is asymptotically tight. Let me conclude with some open questions. This line of work with assumption, distributional assumption based on statistics that are given as input to the seller, we believe that it gives rise to a lot of interesting questions, and here are some. Of course, the most ambitious one would be to try to generalize our results, which are single bidder multi-item, and Azar et al.'s results, which are multi-bidder single item, to the most challenging and general case of multiple bidders, multiple items. It would be very nice to have some characterization there of the optimal mechanism. We assumed that the seller knows in advance the means and upper bound of standard deviations. So we said that in particular that she knows in advance the means exactly. And this might be not realistic. So in practical scenarios, we are not going to be able to obtain the means exactly, but instead we will probably be able to have some interval of confidence on these means. So if this changes and instead we're given some intervals of confidence on these statistics, what does it change? So how does the design of our mechanism change, and how does this influence the robust approximation ratio? Of course, it will be very interesting to go beyond additive Bayer. So what happens in broader class evaluations like submodular or subadditive? And finally, here we studied a setting where we know the first and the second moment of a distribution. What happens if the seller has knowledge of higher order moments? Carrasco et al. Touched a bit on this topic and gave a characterization for the case of n equals 3. So we know the first 3 moments of the distribution for this. Using as objective this maximum robust revenue. And the interesting question that arises here is what is the dependence of our robust approximation ratio on the number of moments n? And does it converge to optimality, this ratio? And at what rates? And we could term this question something like, we could say, what's the moment complexity of robust revenue maximization? Thank you very much for your attention, and I'm very happy to answer questions in the live Q&A.